Thank you. This is a bit loud. OK. So hi, my name is Andrew. If you have problems with the last name, Radev, just remember it starts with rad and it ends in dev. And a radical developer is basically what I am. And I am going to talk about something radical today, static typing, and particularly in Rust. I was inspired by this old talk I went to see. It was about Haskell. Well, Haskell and a couple of similar languages. And it was performed at a Ruby user group. And I had really high expectations for it. I was like, OK, I really like Haskell. What kind of stuff are they going to show us? They're going to show us like algebraic data types and like infinite list magics and whatever. Monads, of course. Everybody loves monads, right? I hope so. The problem was it wasn't like that. It ended up being mostly about like Ruby's issues and about how Ruby is kind of like bad and it makes you have errors all the time. No pointer errors, everything blows up. And as it turns out, we were told that it's mathematically impossible to have errors in this particular language, which I do not really think is true. I guess it depends on your definition of errors. But there's a lot of issues that no math can save. In general, there was this undercurrent in that talk that your language, this dynamic language, it just has too much freedom, and you can't be trusted with it. You need to be limited for your own good. Now, the thing is, here's the thing. I've been writing Ruby for a long time, OK? And when I was learning Ruby, somebody asked the teacher, all right, this whole dynamic thing is great and all, but what if I have this method that expects a dog, and then what if I give it like a cat? What happens then? And then the teacher said, don't do that, I guess. The thing is, nobody wants to blow things up in production. Nobody does these things intentionally, except for laughs, I guess. This is why in the Ruby community, we just have processes and tests and like a culture of peer review to just avoid these kind of issues. Some discipline, I guess. And all of these things are very useful in all kinds of languages, really. A bit less maybe in statically typed languages, right? But I will admit there are some things that no matter how much instructions you put, it's probably a better idea to just fix them, OK? Just don't tell people to hold it by the bottom. Just fix the issue, OK? And Rust has been built, at least in part, to fix some of these kind of issues in C and C++ to avoid memory issues, to avoid hanging pointers and no pointer errors. But this isn't what I want to talk about. This is what I wasn't interested in when I was looking at the talk about Haskell. What I was interested in is not so much, what are the ways that static typing is going to save me from myself, but rather in what ways does it actually give me power? In what ways does it free me to do cool stuff? I think safety is an important issue, and I think we've talked about this, and we'll talk about this a lot more, particularly in Rust. But right now, for these 40 minutes that I have, I'd like to talk about positive features that I found in Rust and in static type languages that give me more freedom rather than less. And I want to start with a very small one, a very simple one, the humble enum, which has much cooler names in other languages, but in Rust we just have enums, I guess. Now, an enum at its core is a very basic thing. You have an enum called weekday, and it has 5 different variants. So different variants of the enums, it can only be one of these variants. Any instance of the enum can be only one of these 5 things. It gets a bit more interesting when you add some data. An IP address that can be either v4 or v6. This is straight from documentation, very simple, very basic. You can do that though. You can have an IP address that is one of these 2, and it doesn't hold all the data. It just holds the subset of data that it requires. So that's cool. And enums are sort of a fundamental building block in Rust. One very common one, the core enum, is the option one. Option encodes optionality. It is the replacement of no in the Rust language. And the way it's used is, something can either be, something, or it can be nothing. And if it's something, we can pull it out with some pattern matching, say if let some value, and then call some sort of a function that returns an optional value. Now, it's a bit maybe safer than just using nulls, because you're forced to pattern match it. You're forced to evaluate this value. And you need to do something similar for results. Result encoding errors and successful results of operations, either an OK or an error. So let's say we have some sort of a file reading function that returns a result. We open this file, and we get a result, and we need to do something with it. That's great, but here's an idea. What if it wasn't a single value? What if it wasn't an enum? What value does the enum actually bring? Could it be just a pair of values, like a value and an error? Maybe the error could be nil if there's no value, right? We could do that, and the nulliness is a problem. But as I said, I don't want to talk in terms of safety. What kind of benefit does the enum bring you in this particular situation? Well, one really cool thing is you can call methods on it, because it's a proper type. The read file function is going to return a result, and we can call the or-else method, which is defined on all results. And the or-else method is only evaluates its argument if the previous result was an error. So we can, we can try to read the settings file. And then if that fails, we can try to read some other file. Like we can put like 5 different fallbacks. And then if any one of these succeeds, and only if any one of these succeeds, we can actually parse this JSON into a settings object, and then sort of pull it out or pull some sort of a default. All of these methods do pattern matching, but they allow us to take this pattern matching and then sort of squeeze it into these individual methods to have this nice little flow that is effectively error handling free. It doesn't have to do any explicit error handling, and it's a very particular case, to be fair. Right? So this is nice. It's useful. But we could do this in Ruby. We could do this in a dynamic language. We could just instantiate a class and give it a value or an error, and then we can even define an or-else methods in basically the same way. If there's a value, call the block. If there's an error, call that one block. We can instantiate the result with a successful value or with an error, and it all works the exact same way. So what value does the enum bring? Well, the problem with the Ruby example, the dynamic typing example, is that you can actually call a result, like you can actually instantiate a result with both a value and an error. I mean, what do we do in this case? What is the logic here? The and then and or-else methods are both going to be called. Does that break any assumptions? It kind of does, right? But these assumptions are not written down in the code. We could add runtime checks. We could throw an error message saying if there's both a value and an error, explode, right? This isn't supposed to be happening. But it becomes a lot more complicated with more complicated enums. You might have an event that has 5 different types, and each of these types has several sort of subsets of results. And this is a lot easier to express in an enum with the different types and the different bits and pieces. Now, why wouldn't the dynamic language have an enum, though? It should be easy to just design the language to have one. It shouldn't be that difficult. Well, the dynamic language doesn't need an enum, kind of. You see, an enum is basically something that allows you exclusivity. Like, types in dynamic languages generally are containers, whether built-in classes or pairs or lists or whatever. An enum actually gives you the ability to say it is actually one of these things. It is not just a container for all of these things. And in a dynamic language, we wouldn't need that because we can just define both types. We can have a success type and an error type, and we can define both the and then and or else methods in the appropriate ways. This is the essence of duck typing, like a pretty popular dynamic concept. It doesn't matter that these are 2 different types. We can, in dynamic typing language, we can just use any one of these. As long as they have the same methods. The problem is we need to know that they have the same methods. We need to maintain the same methods in both of these types. This is an implicit piece of knowledge. We need to be aware of this. And it's the same case with the result. We need to be aware that a result, in this Ruby example that I showed you, should have either a value or an error, but never both. In a static typing context, we can actually say a result is either this variant or the other variant. We can actively express this in code rather than expecting people to read it from documentation or to infer it or to sort of guess it. So, and this is the fundamental difference between dynamic typing and static typing. Dynamic typing relies a lot on implicit knowledge, whether it's string labels that you throw around, whether it's these rules and guidelines that you just sort of need to know. It's folk knowledge. Whereas in a static typing, while you do need to put more stuff, more type annotations, this actually means that you can encode rules and behaviors in the application, and the person that reads them next can actually have them sitting there in front of them. Now, I'd like to open up a bracket here and say this does not mean that the implicit case is bad. It's not a dynamic typing is bad kind of talk. Keeping the rules implicit sort of implies a certain. Some of these rules are just common sense. Like the fact that the result should not accept like both a value and an error seems like something that people should realize, right? More than that, implicit rules means that you can actually make them more complicated. Some of these things you can't really express in a type system. There have been attempts, preconditions, postconditions, but it gets complicated really, really fast. And it's a lot easier to just tell somebody, don't instantiate this method with a cat, than to try to build this, to encode this into the type system occasionally. And it also means that it could be actually easier to patch these rules because they're not written down. For instance, I did say that the result shouldn't have a value and an error, but why shouldn't it actually? Couldn't you have a process that produces some sort of a result and also like a list of errors that occurred during that result that maybe can be ignored but should be logged or something like that? I mean, remember that in the dynamic typing context, we didn't even specify a type for the errors, so we could just have a list of errors maybe. Maybe this could be a workaround while we come up with a better abstraction. Though it is something that we need to be careful about. It does tend to create some technical depth. And speaking of patching and also of being careful with things, I want to talk a bit about monkey patching, or as it's occasionally being called, freedom patching, which is very thematical to this talk. Now, freedom patching is the idea of sort of reopening a class, reopening some sort of a class, and just replacing some sort of a method with some other method. This is super useful for testing, for stubbing. It's also useful for fixing bugs and security issues occasionally, when you learn about them. Just sort of open up some code coming from a library and fix it manually. It works for a time. For example, it also allows you to do some really cool stuff. Like in Ruby, you can open up the true class, which is the class of the value true, and you can define these two methods if true and if false. And you can do the same thing for false class. And you get this cute little sort of expression, like you can have a boolean, and you can call if true on that, and if false, and you get like a new kind of if statement, kind of, right? Like a postfix if statement. It's a really clever trick that comes from Smalltalk, I think, as an example, that is just a testament to the powerful dynamic nature of the language, right? It just, it allows you to change the syntax of the language, to add new syntax that sort of looks like it's always been there. If only we could do this in statically typed languages. Well, as it turns out, Rust does allow you to define a trait called fancy if with two methods, and then you can actually implement that trait for a built-in type. This is a thing that is allowed to you. And so if you do that, well, you basically get to the exact same thing. Like, no dynamic typing needed, no monkey patching actually. You get this if true and if false methods, which do not seem, as pretty maybe, like in syntactical terms, but they're the same code. So this isn't exactly monkey patching. I'd call it core extensions, or extending the core types. More pedestrian name, but the reason for this is, well, for starters, you can't override existing methods. You can't patch over existing methods. You can also not add new state. You're literally just defining a new method that sort of desugars down to a function call with the first argument being a core type. It's as simple as that. Which does give you something very special and sort of different than monkey patching. It gives you modularity. You see, Ruby has struggled with this for years, for so long. If you require some code that patches the core string type to provide a pluralized method, it's really convenient, it's really useful, but now that method is everywhere, just everywhere. Like everything else that requires this code has that method. And this is partly because Ruby doesn't really have a module system, but even if it did, well, string is patched at runtime, and it's a globally accessible core type. So there's not much you could do to keep the sort of expectations of monkey patching and also modularize it. Refinements are one solution. I'm not going to go too deep into it. They're not very widely used in Ruby, but consider it just like a throwaway note. I don't want to go too deep into Ruby at this time. The thing is, though, you can do the same thing in Rust. There's an inflector package. You can take this package, and you can have this, these pluralized methods, and they're there, they work. And this code is perfectly safe to export in some sort of a package, and somebody else can use it without needing to import the inflector. this change is perfectly localized. So there's a bit of a trade-off here. There's a cost and a benefit. The use statement that we use here only affects this file or this module, or you can even affect like a limited scope, delimited by curly brackets. And if you think these are all sort of playful examples, toys, here's a really cool example that I think really changes the language. There's a package called itertools, and if you've written some Python, you've heard about itertools. Other languages have this kind of package as well. It adds on stuff to the built-in Rust iterator trait. You see, in Rust, you can iterate over strings, you can iterate over vectors, or like any kind of collection. With particular methods that give you concrete types, and all of these types implement the same interface, iterator, the same trait. And this is useful. This is very useful because the iterator trait gives you a consistent API to work with collections. And what the itertools crate, the itertools package does, is it goes, and this is just literally just a line in the itertools crate. It just goes for all of these types that also implement iterator. I mean, almost all of them, I guess. Just implement itertools as well, and you can actually do that. You can just put that in your, in your package, put it in your module, import it, and now you can just get an iterator over some string and then chunk it up into 7 character elements, and then put some table characters inside it or whatever. And like all these methods come from the itertools crate, and now you get a table with trunk reasons. Right? It's not the best of examples, but listen, there's a lot of methods in the itertools crate. Okay, like a lot of stuff you could do. And this is a certain extension to built-ins that feels like the real thing. This is the thing that both monkey patching in Ruby and sort of core extensions in Rust agree on. This is the sort of the goal that they both achieve. They create new ways to express yourself that look like built-ins. They extend the language in a way. And for Ruby in particular, this has been a lot of these kind of changes have made it to the core libraries, the standard libraries, and like a lot of this could easily happen in Rust. Like you can write some package to do something, you can extend it, extend built-ins, and then sort of distribute it, and before you know it, it's actually a core thing. Everybody's using it, right? And speaking of core things that everybody's using, I would really like to talk about macros, but they're not exactly a static typing kind of thing, so I decided not to go in that direction. I will show you something really cool though. I'm going to talk about return type polymorphism, which sort of feels like a mouthful. I don't know if you've heard about it. Generic returns maybe like sort of is a bit clearer as an idea. It's actually a very simple idea. You have some sort of a struct, let's say a blog post, and you want to search it for some sort of a regular expression. It's easy to implement this. Just search for search the title, search the body, and return a boolean. Right? That's fine. I can write this. I can use this. I can check if my article has an email in it with this email regex. Yeah, we've got an email. That's fine. Cool. The thing is, at some point, I would also like to get the actual match. That would be great, right? But I would like to have both. I would like to have like this one method that returns the actual match, and this one method that just checks if it's there. So what do I call the one that returns the match? I mean, I got the boolean one being called search. I guess the one that returns the match could be search and get. That's a bit clumsy, not very SRP, I guess. It's probably good names out there, but the thing is, I don't actually have to choose. What I can do is I can define a trait and have that trait be generic by its return type. The search method returning a type T. And then go, well, here's a method called search that returns a bool, and here's just the exact same method with the exact same inputs that returns an option string, and here's one that returns a vector of strings. Sure, why not? I can implement them, however I want, and then I can literally just call the exact same method 3 times, except in all of these cases, I ask for a different type of thing. And I don't actually need to specify the return type even. Like in some cases, for the Boolean case, I can just put an if, and the Rust compiler is going to figure out that I want a Boolean, and it's going to call the Boolean function. I can put an if let, like I showed you before with the options. And there you have it. It calls the right function that returns an option rather than the one that returns a Boolean. It is a bit clumsier still with vectors. I wish it was actually possible to do a for loop, but yeah, for loops are complicated enough as they are. It's a long story. Still, you can actually vary the the return type of the function, like the actual function that you get, based on what type you require, based on what type Rust thinks you need. And again, this is a bit of a toy example. Here's something more practical: serialization and deserialization. A package called serde in Rust. If you have these core types, article, comment lists, and a comment with like bits and pieces, you can put a little annotation here that say, all these three, they derive the trait deserialize. This is a little bit compiler magic, but basically it means that all of them derive, like, implement a particular trait. And with that, we might have like a bunch of texts in a JSON format coming in from the wire, from some API or something. And what we could do is we can call the serde from string methods on this import and just say, I want an article or I want a comment list. And it gives me whatever I need. That's it. And this is the great thing about return type polymorphism. It's basically magic. It looks like magic. It took me a while the first time I saw it to really parse it in my head. It's not that complicated if you think about it, but it is so weird to somebody who's used to dynamic typing. You can't say, I want this one article, and this is like a type that you define in your application, and you call an external function from some package that builds up your type based on the data you give it. You can sort of get that from a dynamic language by maybe providing a type, but it needs to, it needs to do some special stuff for you to be able to do that. In our case, we just define the structure normally. We define any methods we want on it, anything else we want, and all we need to do is put this one little annotation. And like magic, the single method is going to return to you whatever it is you need. This is another key difference between dynamic typing and static typing in terms of trade-offs. In a dynamically typed function, a function can return whatever it wants. You do not specify what the function is going to return in terms of types. A function can return a string, it can return an integer, like an array, and that's very useful because it might return nulls or collections that that fit some interface or whatever. But it does mean that you can't really say, you can't really vary the function that is called based on the return type. You can do that in a statically typed language. Like a caller of the function can request a different return type from a function and then call the particular variant. So this gives you one extra freedom when you design interfaces. This actually gives you like the ability to say, I can choose different methods. I might have to choose different methods for this thing, but these things are so consistent. They can just be named the same way. Whether it's the searching or some other, there's a lot of examples in Rust core of this that I do not have the time for, I think. Well, the problem with it is, though, it is magic a bit. It can be a bit magic. It can make it a bit difficult to understand what is going on sometimes. Here's an example. GTK Rust, the GTK Rust bindings, or the GTK bindings first, have this thing where you might instantiate something with a string, and it would ordinarily be no if you don't have a string to instantiate with, but in Rust it would have to be packaged up in an option, so either some string or nothing, right? That makes sense, and the type that is expected is an option of string, right? Now, at some point they did this little bit of magic where you could actually instantiate the label with a string, not with an option string, but with an actual string. And the way this happened is that this wasn't really an option string. It was like a concrete type that implements the trait that is, some polymorphic magic here, right? This worked, and it worked great when it worked. This was the problem. That's why they rolled it back. That when it didn't work, there were some really confusing error messages, like of what exactly it expected and what it is that your thing did not quite implement, right? The second reason that they gave was simply, we'd like to be more explicit in this. We would like to reduce the magic a little bit. Because the thing is, you have this kind of return type polymorphism set up. It's magical, it's great. You might have like a Schrodinger's cat function that returns like a cat in a box. And you can implement it for a living cat or for a dead cat, and you can get whatever of these two you want. That's not how the quantum experiment actually goes, but never mind that. But what if I implement it so it returns a dog instead? What happens then? I mean, I guess don't do that, right? That's the thing about freedom. That's the thing about designing interfaces. It's not, it means you're allowed to express cool, interesting concepts. You're allowed to express things sometimes much more clearly than they would be if you just sort of sat down and you write like all these types and signatures and whatever. But it also can mean allowing you to write bad code. I think this is one of the reasons why dynamic typing gets a bit of a bad rap, because it does give you a lot of freedom, and this ends up being abused. But you can abuse freedom in statically typed languages as well. It's not really a one-dimensional thing, and it's not about type signatures. It's not just like, do I have to write this thing or not? Modern static typing does do type inference, but the differences do run a lot deeper than that. And I think I've managed to show you in at least a few examples that freedom in this case is not really one-dimensional. It's not just about I want to do what I want and return any kind of type you want. Well, sure, but it also means you're now limited to doing other, to not being able to do other things. Freedom in one way means reduction of freedom in a different way. It's not just a value that goes up and down. And so, while I know that all of you are probably convinced of the freedom that you get from dynamic typing, I hope that, at least a little bit, I've given you an idea of the freedom that you might get from a static typing language. Thank you for your time.